Do you have any questions about previous lectures? Mm. Okay, so let us continue the topic about green functions. So today we'll tell about a more complicated case of wave equation, and in this case there are several different green functions, and two of them are called retarded and advanced. And to discuss this topic, we will solve very simple equations, namely ODEs, which can be solved in several different methods, and then we will compare the answer. So let us start from a very simple equation of this kind. Ft is some known function. And we can ask this function to be integrable from minus infinity to plus infinity, and maybe integrable with any power of t. Absolutely integrable. To have everything well defined, but it doesn't matter. So if you have something like this, how can we write the general solution of this equation? Yes. For example, like this, we can write that u of t is integral from minus infinity to t f of t prime dt prime. In principle, plus some constant. But this choice of constant can be f-dependent. So we are writing the general solution of homogeneous equation with zero on the right hand side, plus some particular solution of the inhomogeneous equation. So and we could write equivalently something like this. Integral from how to write it better? Maybe let me write it as integral as minus integral from t to plus infinity f of t prime dt prime plus c1 c2. Of course, they differ by just one constant, which equals to integral of f from minus to plus infinity. But if we choose such a representation, then this representation is not worse. And you see the main difference between this and this is that in this case our solution depends on the values of f in all previous times, and in this case it depends on the values of f in the future. So in this case t prime is greater than t. So this is called retarded, this is called advanced. So it was a super simple example, right? Maybe let us call this U1 and maybe UR and UA. For example, 1. Let us complicate this a little bit. Mm. Let us say that there is a term linear in U, namely, let us write du in dt plus gamma u equals to f of t. So if I remember this general story about classification of PDEs, how would you solve this equation? We know that there is this is not not an equation from classification. So what should we do to reduce it to one of those equations in the classification with change of coordinate or of function? Mm-hmm. Yes. Thanks. Mm-hmm. Yes. Thanks. So we can say that d in dt plus gamma is e to minus gamma t d in dt e to gamma t. So this produces such a shift. Or we can simply write that u is u tilde times e to minus gamma t. In this case, d du tilde in dt times e to minus gamma t plus gamma u tilde e to minus gamma t minus gamma u tilde e to minus gamma t equals to f. And these two terms simply cancel. We have just one equation. That du tilde in dt times this exponential equals to f. So we can write it as du u tilde in dt equals to e to gamma t f of t. So now we do the same thing. We can simply integrate this equation, and if we restore this exponential, then the answer looks like this: u r of t equals to e to minus gamma t. Maybe let me hide this exponential under the integral. So it will be integral from minus infinity to plus infinity. Oh, sorry, to t f of t prime e to minus gamma t minus t prime. dt prime plus cr e to minus gamma t. And u advanced of t will be over the same integral, but with different limits. Sorry, minus t to plus infinity. So in the same equation. But here we should notice one thing, that this solution is much better than this one, because here t is greater than t prime, and if gamma is positive, let me write it here, maybe even a real part of gamma should, it can be positive, and this is sufficient for everything. So in this case, this exponential goes to zero at the lower limit. And such conditions on f are sufficient for this integral to exist. If you look at the other case, then this exponential goes to infinity, and to make this integral well-defined, we need to impose much stronger conditions on f. In a sense, it should be integrable with arbitrary exponential, at least with this exponential. And as you will see a little bit later, it is a natural requirement. Usually, right-hand sides of equations or initial conditions should not satisfy anything that strict. So, is everything clear about these two cases? So, I'm just solving ODs. So now let us solve something which is closer to our topic, to the wave equation. This is 1 plus 0 wave equation. So now we will have second derivative. And so to integrate this, to solve this, we need to integrate twice. And we can integrate again from minus infinity to t. So du in dt, and the integral from minus infinity to t f of t prime dt prime. And so plus one constant, maybe, yeah. And if we integrate it again, u of t will equal to integral from minus infinity to t dt prime. Maybe let us use this variable from minus infinity to t two primes, f of t prime dt prime. So we are integrating in a variable t prime to t2 primes, and then integrating variable t2 primes. This is the derivative of u. So, and the integration of this constant gives c1t plus c0. So there are these two terms. So there is this formula, but I don't like double integral, and I'm saying that it can be simplified. So, and to simplify it, let us draw the following picture. So let us draw this domain of integration. So we have two variables, t prime and t with two primes. And this domain is described as follows: that T2 primes should be less than T. T2 primes should be less or equal than T, and T prime is less or equal than T2 primes. So there is one restriction, and there is also this line. So H prime is less or equal than T 2 primes. So it leaves us with this domain. I'm doing this because if we draw this picture, we can now exchange to integration limits. In a sense, we can first integrate in T prime and how to say this better? What is first? What is second? Well, we can exchange these two integrals so that we first compute this function of T prime and multiply it by some other integral, and then integrate in to prime the result of this integration. And it can look simpler. So, namely, one of these two integrals will be computable. So, let us write this. So, I'm simply exchanging these integrals. And maybe let us draw two pictures side by side. No, maybe it's too much. So this outer integral is in dt prime, and lower integral is in dt2 primes. So who can tell me which limits I should write for this inner integral? So T prime is fixed. We will integrate in it later. Or maybe let me finally draw this picture. No, maybe it's not very helpful. No, because this blue domain is our domain of integration. So if you fix some specific value of T prime, for example here, what is the domain for T with 2 primes? So yes, thanks. Integral from T prime to T. And what is the limit for T prime? Sorry, for T from T prime to T. Yes, thanks. Because when we go further, then this domain simply disappears. It shrinks to point, and that's all. So, with this formula, f of T prime plus C1 t plus c0. So this is that advantage I was telling about. Originally, both integrals somehow involved t2 prime, so it was really double integral. But if you look at this integral, can we compute at least the inner one? Yes, and so yes, it becomes integral from minus infinity to t dt prime t minus t prime f of t prime plus c1 t plus c0. Uh, so and it's easy to believe that if increase the order of derivative here, we'll still get such kind of result with a single integral of f multiplied by some function. So, and if you now try to express everything in terms of green functions, in a sense, if you write that this partial solution of the ODE is given in terms of the green function. In a sense, if you write that u of t equals to integral from minus infinity to plus infinity g of t minus t prime f of f of t prime dt, then let us list these green functions. So for the operator d in dt, there is g retarded, which is heaviside theta of t minus t prime. There is g advanced of which is minus heaviside theta of t prime minus t. Right? d in dt plus gamma. Sorry, I made a mistake here, t prime minus t. And in this last case, for a second order derivative, the target function is t minus t prime times heaviside theta of t minus t prime. So I don't want to compute the advanced gain function, but of course it can be done in a similar way. So of course we can do this, and we can also continue this list for higher derivatives. So. But so is it clear that these formulas correspond to such gain functions? So this Heaviside theta simply cuts 1/2 of the integral. And of course, a reminder that Heaviside theta of x is uh, 1 for x greater than 0, uh, 0 for x less than 0, and we can put anything here, but for example, 1/2 for x equals to 0. It's a step function. In principle, we can even leave it undefined at this point because it appears only in the integrals with some other functions. Yeah. Yes. So for me, this was a discovery long ago that even if our equation has a higher derivative than first, we can still express its solution using just a single integral. So there is no need to integrate it several times. Okay, so there were all the elementary computations, but now let us try to obtain the same formulas using different techniques. Mm. Namely, let us use the Fourier transform. So, mm, oh, first let us write what the Fourier transform is. I'm using opposite sign for at time Fourier transform, but it doesn't matter. The Theodore of omega. Mm. And so if and the same for f of t. So we see that if we act here with time derivative, then it produces a factor minus I omega. So if we solve the first equation using the Fourier transform, we get the following relation between Fourier images. V tilde of omega equals to minus I omega f tilde of omega. So what is sorry, minus I omega times v tilde of omega equals to f tilde of omega. So v tilde of omega equals to 1 over minus I omega f tilde of omega. So there is formally the solution only, but can you imagine some, for example, generalized function that can be added to this solution? Like, is there anything that uh, we could add to this utility?
What do you want to change?
I'm asking that we have such kind of equation. So is it the only solution of this equation, or can we add something else? Suppose that it is something well defined. It is not, but we will discuss it a little bit later. Oh, have an equation that omega times u tilde equals to some other function. So there is a hint on the right blackboard. We see that yes, but how many deltas? Mm-hmm. But all delta functions at zero are the same. Like there is a single delta function. The, hmm? Hmm? Yes. So we can only add plus c times delta of omega, right? Mm. Mm. And this is because if so there is a remark that omega times delta of omega is zero as a generalized function. This is true because if you take uh, arbitrary infinity function with compact support, like nice test function, and compute this pairing, and then since it can be thought as integral, this omega can be maybe 5 omega, and this omega can be moved to the to the second place to multiply our test function. And further, delta function computes its value at 0. It will be 0 times 5 0. So it equals to 0. And this is true for any test function. So this expression is 0, because we first multiply by omega and then compute the value of this function at 0. So, and it makes perfect sense because the solution should actually be a generalized function. For example, we can compute the Fourier transform of this delta function, and it gives precisely this constant, which we wrote there. But now we need to understand the meaning of this again function that has this Fourier transform. So we call this G tilde. And let us try to compute it in coordinate representation. So g of t is the integral from minus infinity to plus infinity. Maybe let me, well, first let me write it as an integral over some contour. d omega over 2 pi e2 minus I omega t or minus I omega. So mm, the problem is that if you try to integrate naively from minus infinity to plus infinity, this integral does not make sense. They are just at zero. So this contour cannot be chosen as an integral from minus infinity to plus infinity. But we have two other alternatives. We can write. We can choose this contour slightly moved above or below the real line. So let us call this contour target, and this will be deformed like this. It is zero, and the contour goes like this. And for advanced, we can draw it in this way. And let us now compute this two integrals. Mm, so maybe let me draw this contour. It goes like this. But now the question is how to close on this contour. And we have two different options. One is for t greater than 0, another is for t less than 0. So let us first consider this case. When t is less than 0, what is the good way to close the contour so that this function goes to 0 at that infinite part? No, it's for this case first.
zero, we take the upper circle of the arm.
Yes. And because when t is negative, minus it becomes I times positive number, so it should be multiplied by I times another positive number. So omega should go to I infinity. So, we should close it in this direction. And in the other case, we should close it, of course, in the opposite direction, like this. Let us continue this computation. Right, maybe I can erase these solutions. Mm. So this integral equals to zero because our function is analytic there, and this contour does not have any singularities inside. So t less than zero, this is zero, and for t greater than zero, what do we have? Hmm? Yes, this one is obtained in the following way. We have 1 over 2 pi, 1 over minus I. Uh, those are factors in the original integral. Then we have a factor minus minus 1 because the contour is contour goes clockwise around the pole. And then times 1, which is coefficient in front of uh, of 1 over omega. So after all, this is just a Heaviside theta of t. So it's 0 for negative t and 1 for positive t. And you see, also in this case, it's not very well defined for t literally equal to 0, but we don't care because it is just a single point and it is finite. So left and right limits are finite. So, and this is more or less easy to guess what happens for the second contour, because there are only two things that change. First, so the ways we close this contour are the same. The only difference is that now this pole will be inside the contour for negative t. And in this case, integral will go counterclockwise around the pole, so it will change the sign. So we can write that the advanced income function of t is minus Heaviside theta of minus t. Obviously. Uh, okay, are there any questions about this computation? So it was a quite complicated way to obtain the simple formula that can be obtained by simple integration. but at some point it becomes simpler.
Yeah, well, I'm checking which contour to use to make sure the arc goes to 0. I always change it to polar coordinates to see it and make an inequality, but are you doing a shortcut in your head?
Of course, because it is clear that that imaginary part uh, of omega is positive and goes to infinity. So this integral goes to 0 exponentially, and mm, the only thing that needs to be evaluated or estimated are these short pieces around infinity, but in that case, the function, the integral goes to 0. So, mm, like, uh, mm, if omega is of order 1 over r, then this exponential becomes dominant, uh, and when imaginary part of omega becomes of order 1 over r, this exponential becomes dominant, and it is divided by something of order 1 over r. It is multiplied by something of order 1 over r, because it has a real part of this order. So it's easy to see that it goes to 0. Yeah. Well, let's now jump to the third case, um, and go back to a second slightly later. Okay, so now in the third case, all these arguments about contours are the same. The only thing that changes is the function of the integral. So for this right function of t is 0 when t is negative, when t is positive, we need to do the same. 1 over 2 pi minus 1 for the clockwise direction times 2 pi I. Sorry, I also forgot to write 2 pi I here, but times 2 pi I. That cancels all these 2 pi I's. This is coefficient in front of, sorry, 2 pi I times 1. Well, this numeric coefficient times 2 pi I times the residue of this function at omega equals to 0 e to minus omega t minus I omega squared. So this can be computed in the following way. Since we have a second order pole, but we are interested in the coefficient in front of 1 over omega, we need to expand it as a series in omega. So the only thing to expand is the numerator. Residue at omega equals to 0 of 1 minus I omega squared plus t times minus I omega. So this is for order omega squared. This is of order 1. Those are uh, also regular, so we don't care about them. We care only about this term, because only this one behaves like uh, 1 over omega. So this is minus I. So this equals to t. So the green function itself equals to t beside theta of t, because it's t for t greater than 0 and 0 for negative t's. Right? And by the way, we can compute the generalization of this phenomenon uh, uh, for arbitrary derivative. So if you put here dn in dtn, so can you imagine what a gain function for this operator is? So what happens if you replace here 2 by n? Yes. Yes. So it was n. Yes. So later. Mm-hmm. Yes. Thanks. And uh, and even more. So we can say that it is a kind of Fourier transform of we can say that it is the integral operator that corresponds to a negative power of d in dt. So in principle, we can extend this by saying that it is 1 over gamma of n t to n minus 1. But we can also define this for the fractional derivative, because no one can stop us from considering for an image which equals to minus I omega to power alpha for arbitrary alpha. So we can formally solve the equation with d alpha over dt to power alpha and this will correspond to grand function given by uh, by 1 over gamma of alpha uh, t to alpha minus 1 for arbitrary alpha. So it defines a fractional derivative. So uh, uh, we can say that uh, uh, where shall I write this? I can erase this. So d in dt to power minus alpha acting on f is given by definition using this grand function, like 1 over gamma of alpha, integral from minus infinity to t, t minus t prime to alpha minus 1, mm, f of t prime and dt prime. So this works for alpha greater than 0. It also works for alpha from 0 to 1 as long as this integral is well defined. This is also fine. And if we consider positive alpha, so if if alpha is greater or equal than 1, we can define that d in dt to some no, sorry, um, what did I write? Alpha from 0 to from minus 1 to 0. And if you want to consider fractional derivative with positive power of d in dt, then we can simply decompose it as d in dt to power n times d in dt to power alpha minus n, such that this is less or equal than 0. So we first need to act with such a differential operator and with such integral operator, and then differentiate the result.
So you can smoothly deform derivative operators into the identity operator?
What do you mean by smoothly deform?
If you move it towards 0, it becomes the identity, right?
Yes.
Okay.
But in this case, uh, the limit of this expression is not very well defined at the level of such a integral. Mm. because on one side this integral starts diverging, on the other side we have 0 in the denominator. So mm, no, but actually, no, it's computable. We can simply say that we are interested in the main divergence of this integral when t goes, when which comes from the region when t goes to t prime, and then this asymptotics is cancelled by alpha coming from the gamma function. So maybe, yeah, this limit can be taken. Okay, I just wrote this formula, but it can actually be obtained from the Fourier transform uh, of this uh, of this 1 over minus I omega to power alpha. From this power alpha. But yeah, there is one detail that this function with arbitrary fractional power has a branch cut. And the action of this branch cut depends on the way we choose the contour. So if you choose the contour this way, as for a target function, then we should place the branch cut of this power like this. We should send it to minus infinity, to minus I infinity. And this technology of integral computations works like this. If t is negative, then we can still close this contour in the upper half plane, and we don't care about the analytic structure of the integrand. But if t is positive, we cannot reduce it to just residue computation. We should write it like this. We can only deform contour so that it encircles the branch cut. This is for t greater than 0. And this integral can be computed using the following formula, that gamma function has two integral representations. One is this, from 0 to infinity, dx x to ap minus 1, e to minus x. There is one representation, and it can be understood by integrating this expression by parts. There is also another representation for 1 over gamma of p, and this is the integral over the following contour. 1 over 2 pi I integral over negative x's dx x minus p e to p. So this integral can be understood for the case of integer p's precisely in this way, that it takes the p's coefficient in the series expansion of this exponential. In the sense, for those values of p, it reduces to residue computation at zero. So it simply computes m minus first term of expansion, which is 1 over gamma of p. But the point is that this integral works in the same way for all values of p. It's an non-trivial statement that needs to be proved, and maybe we will come to this later. But mm, mm, I haven't decided yet. So, do you have any questions? Oh, no, this long remark that you can define fractional derivatives using the Fourier image. So this is like in linear algebra. If you want to compute some complicated function of a matrix, we first need to diagonalize it. So it acts by eigenvalues, and then compute this function on all eigenvalues and go back to the original basis. So this is what was done here. Mm. Okay. Let us now go back to our gain functions. So this was one remark. So we were able to recover these gain functions, and let us ask about these ones. So, so case 2. So in this case, we want to compute this gain function naively. We need to go from minus infinity to plus infinity, d omega over 2 pi e2 minus I omega t over what? What should I write in the denominator? If our original operator is this. Yes, thanks. Yeah, so in this case, the pole is shifted from the real line from the very beginning. Analytic structure looks like this. With minus a gamma, and there is no need to shift this contour further. So if you compute on this integral, we will get here beside the theta of t as before, because everything works as for the retarded gain function. Times exponential of minus gamma t. So, so we see that although our equation had, in principle, several different green functions, if you saw it naively. This Fourier transform method chooses for us the best one, because uh, another green function goes to infinity at infinity and does it in a bad way. It explodes exponentially. So it cannot be applied to most of the functions. So and so we get naturally just one green function. So we only get a function that goes to 0 when t minus t prime and goes to infinity. So, and it is in a sense understandable, because if we take a green function in coordinate space that goes to infinity at infinity, then its Fourier transform is not defined because we cannot integrate it. And this is much worse than divergence in the delta function, because there is no way to regularize such a green function. So, of course, this pole still gives us a solution of the homogeneous equation. In a sense, it gives exponential of minus gamma t, but it cannot enter the green function. There is no second option in this case. So, are there any questions? So far, we know two methods to obtain these green functions. Uh, but you remember that we obtained the green function for the wave equation even without this. We could simply integrate our equation twice, and in some sense it reminds us the first computation. But now let us see one more approach to green functions, which looks in the following way. We can try to solve an equation they satisfy. I mean the equation with dot function on the right hand side, just as an ordinary differential equation. So for example, we want to compute green function of this operator, and we want to, so we need to solve the equation that d2 in dt squared g of t equals to delta of t. Uh, mm, of course, if t is different from 0, this equation is homogeneous. So it can be solved separately for t greater than 0. In this case, what is the solution of this equation? g of t and for t less than 0. How can we solve this equation? Yes, yes, but we know that our solution is defined up to the linear function, so we can choose this freedom to make this function equal to 0. So we can put this one equal to 0, and here we have g of t equals at plus b. Uh, but if uh, if something has a discontinuity in in the function itself, then its first derivative will equal to delta function. And further differentiation will produce the first derivative of the delta function. So uh, so b should equal to 0 because uh, uh, g 2 primes of t equals to delta, not to delta prime. So first the function itself should be continuous. But now we need to compute this continuity. And to do this, we integrate our equation from 0 minus epsilon to 0 plus epsilon. G prime of t dt equals to integral from 0 minus epsilon to 0 plus epsilon delta of t dt. So this equals to 1, and this equals to g prime of epsilon minus all this integral equals to g prime of epsilon minus g prime of minus epsilon. Okay, so what can we say about a looking at this equation? Yes, thanks. So our rank function is t times Heaviside theta of t. So, and if you look at other answers, they look in the same way. In a sense, they equal to solution of the homogeneous equation everywhere except the point where we have a delta function. And in that point, they have appropriate discontinuity. So in this case, we had a first order operator, so discontinuity was in the value of this function. In this case, we had a second order operator, so discontinuity was in the first derivative. And this method can be used for more complicated cases. For example, you can add here some constant. You can consider higher differential operators. So, hmm? Because we have many different choices for solution. So solution of this equation is defined up to the linear function. So if we are interested in the green function that is 0 for negative t's, then we can use this freedom to cancel whatever appears for negative values. Yeah. But it will actually not be the case for this derivative plus maybe minus some constant. And let us actually look at this case to make it uh, uh, slightly more complicated. Maybe I can erase this. For example, for this method. The nature, if you work with this equation, that then what are its solutions for t greater than 0 and t less than 0? What are the possible options? Like no, I would lose sign because I have chosen this deliberately.
Also, exponentials.
Yes, I can have c plus times e to plus gamma t plus c minus e to minus gamma t. Or maybe let us choose a and b. No, a plus a minus and here b plus e to gamma t plus b minus e to minus gamma t. But uh, if you work with this equation, we don't have all these problems with retarded and advanced green functions, but we have another problem that if we allow this term here and this term here, then this green function will go to plus infinity, and it will be extremely hard to use with any reasonable. Sorry, it should be g with any reasonable test function. In a sense, we would need to any reasonable right-hand sides. We would need to require them to decay exponentially at plus and minus infinity. And to avoid such problems, we should impose boundary conditions saying that this grand function should go to zero in some way. So this requirement tells us that this term should be removed, and this term should also be removed. So the green function becomes known to such exponentials growing and decaying. Then we can say that b plus should be equal to a minus so that it is continuous. So this is for convergence. then B plus should be equal to A minus continuity. And when we have this, we can write that G of t equals to greater than 0 minus e2 minus gamma t. Oh, we can write it as a single expression. E minus e2 minus gamma absolute value of t. And when we want to find a minus, we should look only at a vicinity of 0. So when t goes to 0, g of t behaves as a minus plus a minus gamma absolute value of t. So if compute its first derivative, then it is a minus gamma for positive values and minus a minus gamma for negative values. And we know that this discontinuity should be the same because we don't care about the regular term. So can you say what the value of a minus gamma should be in this case?
I think it would be the term of 1, so we need A to be 1 over 2 gamma.
Yes, and so this range function is 1 over 2 gamma e2 minus gamma value of t. There is an exercise to recover the same expression from the Fourier transform. Yeah, this is it. This behavior is quite different from what we would have if we put here plus gamma squared. In that case, we would have two solutions, and we would need to deal with retarded and advanced gain functions, and we would have even more options because there are two poles, and they can be passed in different ways. So. And that would correspond, for example, correspond to symmetric gain functions that also appear in some contexts in quantum field theory, example. Okay, are there any questions on this? So, so I was telling this actually as an introduction to discussion about the wave equation in 1, 2, and 3 dimensions. So, do you have any questions? Okay, can we go further? I want to study discontinuity of the first derivative of this function. To do this, well, actually, so this behaves somehow, it decays there, but uh, decays exponentially, but I don't care about those values. I only care about the first derivative around zero. So it's sufficient to expand this exponential as a series of first order, because t squared is derivative of t squared is equal to zero. So you compute discontinuity of this gain function, and then look at the previous computation to know what the discontinuity should be. We can do absolutely the same with this equation. We can integrate it from minus epsilon to epsilon and see that right hand side gives 1 and left hand side gives the discontinuity of g prime. So now we compare this discontinuity, which equals to 2a minus gamma, with 1. It gives a equals 1 over to gamma. So is it fine? Okay. So let me use this. Will not compute this gain functions for the equation, but we can at least start. Or maybe oh, yeah, we can start. So we now want to solve this equation. Ut minus Laplacian of u equals to gt minus Laplacian of g equals to delta of t and delta of x. So, and again, we have infinitely many solutions to this equation because we know that this equation at least has solutions that are plane waves. In 1 plus 1 dimension, we have solutions like u of t minus x. In arbitrary dimension, we have the same solutions and infinite linear combination of them. So to get rid of such solutions and to find an eigen function, we should ask it to be one of these two types. Namely, let's choose a retarded eigen function. In a sense, we ask it to vanish for negative times. Of t and x is 0 when t is less than 0. And physically it corresponds to the fact that a solution of our wave equation depends only on the value of its right hand side in the past. So we are not studying any self-consistency conditions or whatever. We simply run this evolution. Like take our string or membrane, which is originally uh, flat or has some initial condition, and then run this evolution. So, but let us at least see when where this equation affects something. So we can compute the Fourier image of this gain function, because we simply replace time derivatives with minus I omega and coordinate derivatives with minus ik, and divide by the differential operator. So gain function is minus omega squared plus k squared. So this comes from dt squared. This comes from minus d minus Laplacian. So do you have any questions about this? So there are problems for k equal to omega by its absolute value. So and can function in a coordinate space. D of t and x is integral from minus infinity to plus infinity d omega over 2 pi d k over 2 pi to k. So we have this integral. And if we want to choose this condition, then we should compute the integral in omega first. So it's very easy to make sure that it vanishes for negative times. We simply need to move this contour slightly above the two poles. So C. Oh, sorry, I wrote from minus infinity to plus infinity, but I should have written integral over this contour. And this contour looks like this: minus absolute value of k plus absolute value of k. So, so and again, if time is negative, we can close on this contour above, and it is 0. When time is positive, we can close it below and compute two residues. -1 for clockwise direction, 2 pi I because it's integral, and then we need to write sum of two residues at omega equals to plus k plus absolute value of k, and let us write this denominator as omega plus absolute value of k, omega minus absolute value of k. Oh, so I should have moved it a little bit. Yeah. So we have this expression, and you see that there are, of course, two first-order poles. So when we compute residue, we need to hide this term because we are looking at the coefficient in front of 1 over omega minus absolute value of k, and substitute absolute value of k everywhere else. So let me. Oh. So what is the residue of this expression at omega equal to k? Oh, what? 2 pi was here. It was taken into account. Hmm?
k times e to the I minus I, k t plus x over 2.
No, not t plus x, because we are in the multi-dimensional case. This is the absolute value of of uh, of this vector. So k is a multi-dimensional vector, and this domain in the k omega space is a cone. Maybe better to say a pair of cones. Like this. So mm, this is the omega. Well, kx, ky, for example. If it is a three-dimensional case. So if you fix some point in the k space, then there are two omegas, one positive and one negative, that correspond to this in this k. So Okay, k vector and absolute value of k are two different objects. One is a set of number, another is just one number. So and omega equals to absolute value of k, or minus absolute value of k. Is it okay? Uh, So yes, it's minus I absolute value of kt plus ikx. Do you have anything in the denominator? Mm, yes. Yes. Absolute value of k. Mm. And what about the second term?
e to the I absolute value of k t plus I the first power of k and x divided by 2 absolute value of k.
Was yeah, was a plus sign. Thanks. Okay. And by the way, if you were interested about the Euclidean function uh, this equation with plus sign, you can see it here. Because at this stage, I can say that, okay, let us forget about the outer integral. We are simply solving this equation with uh, k squared and put x equals to 0. So we will have this we will have this sign of kt over 2k times Heaviside theta. So, so we can, in this point, we can write another example that d2 squared minus plus k squared g of t equals to delta of t gives the range function of this kind. Maybe k over 1 over k sine of k t Heaviside theta of t. So it's like the first function t times Heaviside theta, but replaced with solution of the homogeneous equation. But so it would be the final step in that case. But in this case, we still need to compute the k integral, and we will do it tomorrow. Okay. So it's maybe the most technically complicated problem, but it's nice to do because it has physical consequences, and it tells about behavior of this equation. Okay, thanks for your attention.